Well, that's quite packed. I'm really happy that so many of you decided to join this session right now. I've got a few more seats here in the front row if you want, but if you're happy in the back, that's also fine by me. Okay, excellent. Well, I think this might be the session with the most overhyped technology during this conference. So what I'd like to do is to take a bit from this hype out of the technology, because I think that there are very interesting cases behind the hype. And so let's get started. Let's spend the next 60 minutes to look into what blockchain really is from a technical point of view. I assume that most of you are software developers and software architects. That's also my original background. Well, my name is Ingo Rammer. I co-founded a company called ThinkTecture a while ago. And on the blockchain side, that's my current personal focus. So I work on blockchain side from the code level, so very deep in the technology, up to ISO TC 302, which is an ISO technical committee trying to standardize 307 to standardize blockchain. And from the technologies I've worked with, the hands-on experience are mainly based around the Hyperledger set of projects. That's an open source tooling, especially Hyperledger Fabric. Hyperledger has multiple blockchain tools. And we are also a member of the EEA, of the Enterprise Ethereum Alliance, so we have some knowledge with Quorum, with their idea, or JP Morgan's idea of blockchain. The most interesting part for you might be our web address. There is a section to conference slides, and I will to conferences, and I will upload my slide deck right after this conference. You can download this. Okay. Today I want to talk about technology. Because, you know, when we are, as developers, when we look at blockchain, what we get is a lot of hype from our business stakeholders. So sometimes they are misled because somebody else tells them that all their business will change based on blockchain. And of course, you have such a trickle-down panic. And well, as we know, sometimes business stakeholders need a bit of guidance. And that's what I want to give you. Something which you can use to talk with your business stakeholders to tell them what's really behind the hype, what's the technology behind the hype. And that's the main part of today's session. And at the end of the session, I want to talk about 3 different use cases, or classes of use cases, which we think are interesting for existing businesses. Because a lot of the hype is based on ICOs and investment, and 90% of it is scam. And some of them might be successful, some of them might not be. But I'd like to talk about things which companies can do today to get value out of this technology. Okay, so let's get started. There is one case which I'm going to refer to throughout this session to explain a few concepts of a blockchain. And this case is the porting of mobile phone numbers from one provider to another provider. Because in theory, this should be very, very easy. In practice, it's not. So that's not a use case we implemented. It's just something which I used to talk about. Okay, so when we look into phone number porting, what's happening is it starts with myself and my phone and my existing telecommunication provider. And I've got a contract with them, and they know a few things. These 3 things, the phone number, my date of birth, and the name, are the criteria which are legally required in Germany to trigger the porting of a phone number. So that's the reason. Of course, they know a lot more, but they know this. And when I want to get a new contract, I walk up to a new provider. Let's say I am at T-Mobile and I want to switch to Vodafone, and I'll sign a new contract with them, a new contract for the same number. And then my new provider has to contact my old provider to tell them that I want to switch. And they are doing this using very sophisticated technologies. The interesting thing is that it's 2018 and they literally do this by fax, by sending facsimiles. That's fantastic. When I looked into this for the first time, I was blown away. We as technologists, we always expect that the world should be very technologically oriented, but sometimes they are not. Okay, my provider sends me an SMS, email, or letter or something because they have to inform me that there is a request for a transfer and I have to okay this request. Reason is, my old provider has to tell me that I still have to finish paying for the contract if the minimum contract duration has not been met. That's all specified by law. And so they have to send me some information, I have to okay it to agree with these fees. Okay, now that's fine, and at the end, we'll get some facts sent back to the original telecommunication provider, to the one which requested the transfer, where I want to go to. Now that's nice, and we all know this process works flawlessly all the time. And most people think that, the telco providers, they want to make this explicitly hard for us to keep us as customers, but that's not true. The reality is, when you call one of them, they will tell you their point of view. And their point of view is, from our side, everything okay. We sent our facts, we don't know what happened. You call the other side. The other side tells you exactly the same thing. They don't do this because they want to screw with you. They do this because they have literally no process transparency to the other side. So this fax sent from telco B to telco A might have been lost. So telco B says, well, I sent the fax, for me everything's okay, now I'm waiting for response. The other side never received it. So they say, well, from our point of view, you don't even exist. There is no transfer record for this. Okay, so that's our starting point. We have no shared information between these two companies. We do have a bit of shared information in Germany. There's a system created by T-Systems quite a while ago where you can look up who owns a certain phone number. Phone companies can look up which phone company is responsible for this, but it doesn't capture the whole process flow between these two companies. Okay. So how big is this problem? Just so we can estimate, is this real or not? Well, the problem is that normally when we think about this for the first time, we say, well, it's easy. They should just create service-based interfaces between those telco providers and everything's fine. Reality is there are more than 3,500 telco providers in the meantime. This is an older number. There are voice-over IP providers located in Cyprus who have a handful of customers in Germany, and they have to take part in this number porting scheme. So that's what makes it harder. And then the Bundesnetzagentur, the German regulator, spends a lot of time and energy to escalate this and to provide an answer. You know what an escalation is? A Bundesnetzagentur escalation is. And we see that a lot of the reason we are paying tax money for this are these escalations. An escalation is, you say, well, my provider didn't port it in time. The Bundesnetzagentur calls up provider A, provider B, and you, and it brokers a conference call at the end of the day, so that everybody can express their view of the world. So we have a reconciliation stage, and that's very typical of existing IT systems as well. Even if you share data in an electronic way, there is a stage of manual reconciliation if we figure out that, for whatever reason, our worldview differs. Okay. So the scenario we are looking at is one where we have a number of independent actors. We have telecommunication companies, we have a regulator. They don't want to work together. T-Mobile has no reason of wanting to work together with Vodafone. The regulator tells them that they have to do this. We have varying levels of trust between the participants. The telcos, the individual telcos, they don't trust each other. T-Mobile would never hand over their whole set of data to a competitor. They might trust the Bundesnetzagentur, the regulator, but the regulator certainly doesn't trust the telcos. I mean, it's a regulator after all. Okay, we want to have some kind of transparency because the reason for this problem, the time and money wasted on the regulator side and for each individual telco is massive because we have no transparency. So we would like to have some kind of transparency. And we would also like this without introducing a central authority. That's always a grand theme in terms of blockchain, that you want to run this decentralized. You don't want to create a new industrial consortium which has to go to T-Systems to tell them, create this database for me. But it runs decentralized. Okay. I'm going to refer back to this sample throughout the next 40 or 50 minutes. And first, let's get started. What is a blockchain? Well, that's the Wikipedia definition. And it's a nice starting point. It doesn't answer too many questions. It doesn't answer any question of why blockchain will change the world and make it a better place. And the reason is that this definition only refers to the data structure, to blockchain as a data structure. And essentially, this is blockchain as a data structure. When a technical person talks about a blockchain, that's what she or he should refer to. We don't do this. We usually, when we say blockchain, we mean a blockchain network, a network of nodes operating a blockchain. But in reality, a blockchain is just a data structure where you have a certain block which has maybe configuration information, some content, and for which we generate a hash code over this block information. And this hash code is then used in the next block, in the header of the next block, to refer back to the first block. And then we add content for the next block, and we create a new hash, a new checksum to make sure that nothing here has changed. And this is repeated over and over, millions of times. So, and the important part is always this hash combination. So every new block refers to the previous block. And then the whole thing is hashed again. The reason why this is important is because this is what makes it relatively tamper-proof, or at least tamper-evident. We see if somebody tries to change data after the fact. If I have 1 million blocks here, and I go to block number 500,000, and I change any information in the block, its hash will change. Given that the hash of this block has been changed, all the following blocks become invalid, or would in theory become invalid, so we can detect if data is changed after the fact or not. Okay. No, that's not so nice. Oh, it's gone. Okay, perfect. So that's the blockchain. Now, when we're talking about blockchain, in reality, we are talking about a blockchain network. And that's the important part about the blockchain. And that's how all these blockchain toolings differ. And what's happening is we have a number of nodes. And over time, some of the nodes will be selected by an algorithm to be the one who can create a new block. I'm going to talk about these algorithms in a second. And after the new block is created on only one node, it will be replicated in a peer-to-peer replication manner over to all the other nodes. And then the next block will be created by the same or by a different node, and usually by a different node, and it will replicate again. So over time, we have basically we have an eventually consistent data structure, because over time, each node sees the blockchain in exactly the same way. So we all achieve exactly the same view of the world. Okay. Important for this is all these nodes are operated independently. There is no central web server or database server which runs this. In essence, we have a huge replicating database here. Okay. Now, when we're looking at these databases, there are two, or at these blockchain networks, there are two main ways of operating a blockchain network, and they are fundamentally different. So if there are only 3 things which you take out of this session, that's one of them which I'd recommend you to take out of this session. There are 2 types of operating models which have nothing in common. We have public blockchains. That's what we usually talk about. We have Ethereum, Bitcoin, one of the public chains. They can operate, or some of them can execute smart contracts, some of them can just store data. But what they have in common is that they are so-called permissionless public networks. So nobody has to give you permission to become a node inside of Bitcoin or to become a node inside of Ethereum. You just download the node software, install it on your machine, and you can start the node software. The node will connect to a number of known name server style nodes to find out which running instances exist, and it will connect to running instances. Should this discovery process fail at some point in the future, you can just tell your node the address of one existing node. So as long as there is one node running, you can connect yourself to this network. And then you will start to synchronize the data to replicate all the existing blocks to your node. And that's a network which is, and then you're a full node. And just like all the other nodes. And then, well, these networks change over time. New links are created. Some nodes disappear because somebody just shuts down their node. New links will be created so that you have a sustainable number of links between any set of nodes in there. Okay. We know this from Ethereum, Bitcoin. That's your classic thing when we talk about public blockchains. Now, there are different types of blockchains, and in practice, we see a lot of those. We see more successful, by orders of magnitude, more successful blockchains in the private space. The thing is, nobody talks about them because they are usually industry specific. So if you are in the industry, you might know that there is somebody working on a blockchain for this industry. If you're outside of the industry, you usually don't see them. And you can't invest in them. They don't have an ICO. There is no coin behind them which you can trade or exchange. Well, there could be one, but that doesn't have to be. The main difference is that the participants are known. So here we have our telecommunication companies and we have our regulator. So that's a key difference. Because if you know who is in the network, you can remove somebody from the network. You can't remove anyone from Bitcoin or Ethereum, because even if you would technically remove them, they could restart their node software, get a new ID, and they be someone different. You can't do this here. Okay, so private chains are governed very differently from public chains. In a private chain, if you want to join the chain, usually there is a governance process. This could be a democratic vote, or this could be a single entity which, by definition, has the right to admit new members. So if you look at our telecommunication sample, if you want to join, you basically try to find out who's responsible for this. And let's say in our case, the Bundesnetzagentur would tell you that this is the law under which this blockchain operates. And by the way, that's the set of contracts you have to sign to be allowed to get on the network. So you sign your contracts, and then the network will be reconfigured to allow you to connect to it. It's like you getting a username and password. Of course, you get some other kind, technically you get some other kind of information, some credential, but you can imagine it's like you getting a user account. In other networks in which you don't have a regulator, and if you don't have a legal base for operating this network, there could be a majority vote in code. All of this is implemented in code. So getting the access credentials here really reconfigures the network to allow you to connect to it. Okay. So if you have a majority vote, this would also be implemented in code. When you start the network, you define a certain governance process for your network, and you implement the governance process in code. Okay. These kind of blockchains are usually run by consortiums, by industry groups, by interest groups, by governments even. There are some governments which are very, very forward in this, and they run blockchains for their own government institutions. Okay, so a public blockchain has a number of key properties, and they are also their biggest point of criticism at the same time. Number one, we don't know who is on the network. That's the good thing. That's the whole idea of Bitcoin. It's a censorship-resistant network. I cannot censor your transaction. If you want to send your Bitcoin to somebody else, that's going to happen. Nobody can block this transaction. It's not like the regular banking system where banks are legally required to withhold funds. If you get an international sanction, let's say a UNO decision is made, then your funds will be withheld. That's not possible. So this means that we still need some way to secure this network, because if everybody can do whatever they want, and they can try to attack the network. Attacking a blockchain network means you are trying to feed incorrect information into the network. I'm going to talk in a few minutes what incorrect information means, but just assume in terms of Bitcoin, this would mean that if you are the one who is selected to create a new block, you try to put in transactions which tries to send money from all of us in the room to one person. So that this would be an attack on a network. This attack is prevented or reduced. The attack surface is reduced by making it very, very expensive to do this. Because to attack the network, to really get the network to agree on your new block, you would have to own, in Ethereum or Bitcoin's term, 51% of the compute power behind the miners, behind the mining process. Now, mining is something I haven't talked about before, but I think most of you will have heard about Bitcoin mining and the massive amount of CPU and energy waste which goes into Bitcoin mining. The interesting thing about Bitcoin mining is all this energy waste is spent not on processing transactions as such, but is only spent on securing the network. Securing the network means if we have 25,000 nodes connected at one point in time, we need to find out who is allowed to create the next block before we start to synchronize it. And the whole CPU consuming element of Bitcoin or Ethereum is a massive random number generator. It's a random number generator which is programmed so that it's weighted by how much money you put in. So if you put in more energy and more hardware, and more advanced hardware, you get selected more easily. And and then you get selected. So all the energy is wasted. It's not used for transaction processing. It's only used to operate the world's largest and slowest random number generator. It's slow by design. It should only generate a number or one element, select one node every 10 to 15 minutes on Bitcoin, every about 10 to 15 seconds on Ethereum. Okay, so we have this problem in a public chain. We have the fact that all the data is public, so that's just all the Bitcoin transactions should remain public so that you can't retract them. And we have very low transaction counts. If you're looking at Ethereum and Bitcoin, we have less than 20 transactions per second globally for all users of the network. All smart contracts on Ethereum of everyone can only handle 15 transactions in total per second, approximately. So that's quite an interesting property. How does this look like in private blockchains? Well, we know the participants. So we have a technical way to prevent access to the network, to remove access if somebody behaves in a harmful way. Therefore, we don't need any mining. So that's one of the key takeaways. For private networks, you don't need mining. If you operate today, if some of you are already operating private networks and you're using mining, which is basically you're just using gas or one of the other Ethereum derivatives to run your private network, and you have configured it so that it uses Nakamoto consensus or regular mining, you're doing it wrong. The reason you're doing it wrong is because somebody could attack your network just by putting in more hardware. And if you're running a business-to-business network, that's not what you want. It's not enough that you tell all these telecommunication companies that they should run their own node and they should promise that they only put in one server. No, because if the incentive is high enough, I might hire a big bunch of servers on Azure or on Amazon, on AWS, just to take over the network. And you don't want an arms race. That's not reasonable in business-to-business scenarios. Instead, you will work quite likely with a proof of authority scheme where blocks are signed by a known digital signature, which you have received during the joining phase. Because again, the whole idea of the consensus at that stage is to find out who can create the next block. And we shouldn't, in a business environment, you usually don't want to waste resources on this. Transactions in these networks can be public or private, depending on the infrastructure, or depending on the tool which you have used to implement them. So there is a way to send transactions to only one participant or to the ones which really transact in this transaction. You don't see the full record on the public blockchain. And given that we have a different consensus protocol, we can achieve way higher transaction counts. So you have transaction counts which are very similar to what you would expect from a database in a lot of cases. So these are key differences. It's very different from what we normally know as a blockchain. The technologies for this are, for example, Hyperledger Fabric. Hyperledger is a project of the Linux Foundation, and Fabric is one of their blockchain toolings. They have more for different use cases. If you today buy your blockchain as a service from SAP, IBM, or Oracle, it's also quite likely that behind the scenes you're actually paying them to run Fabric for you. That's because they are big sponsors of the project, and especially IBM invests a lot of time. And then we have Quorum on the Ethereum side, which is a Ethereum derivative which also supports private transactions and which supports way higher transaction counts. Okay. So if we just look at this, at that point, one of the questions which is important to answer is, how do you connect to this network? So we have now figured out that we want to start a network, and we have participants, but where are the clients? And well, you can imagine that this looks more or less like a database. So just assume that the whole blockchain network is one big database, and you have a client SDK, like you'd have a JDBC or ODBC SDK to connect to your database. You have a similar thing to connect to one node. So if you look at a network where a telco operates a node in their own data center, they can connect directly to their node. Or you could run it inside of one of the cloud providers just as virtual machines. Or you can, of course, cross the boundaries between your local data center and the cloud provider. Or, and there's also a case if you're if you're one of the 3,500 telcos who don't have major stake inside of Germany, you quite likely wouldn't want to run your full node. The cost involved here would be too high if you only have, 10 number transfers per year. So you could connect to existing nodes. The important thing here is that if you connect to a node, you're basically trusting the node that it gives you, that it shows you the correct view of the current state of the blockchain. So that's one decision you have to make. Otherwise, you'd have to run a full node. However, this node cannot impersonate you. That's the important part. Otherwise, nobody would do this in Ethereum, because if my node behind the scene could impersonate me, it could siphon all the money away from my account. So the important part is the clients here. They have the private keys. They are the ones who sign the transaction, not the node. The node doesn't sign the transaction. The client signs the transaction. Technically, you can operate the node so that it also is its own client, but conceptually, the client owns the credentials, not the node. Okay, so I talked a bit about blocks so far and how blocks are synchronized, how networks are built. The question is, what is in the block? And if you take the three things home, this would be maybe the second thing to take home. And now I'm building blockchain semantics up from the very bottom layer. And at the lowest level of a blockchain, what is in the block is just a signed statement. It's just somebody saying something which is replicated worldwide so that the person the entity or the client which said it can't take it back or change it later. That's, by default, that's the starting point. There's no logic in it. We don't have checks yet, etc. But we start with this. We have statements which can't be retracted. So if we look into our sample, into our private telecommunication porting case, a statement could be that one particular customer might want to transfer their number from telco A to us. In this case, the sender, the signer would be telco B. And you would take this statement and put it on a blockchain. No matter which one, these are technical details, I'll come back to those later. And telco B, the receiver, will have an application running, a service process running, which listens on events from the blockchain. And whenever they see an event like this, where they are the destination, they will trigger internal processing, off-chain processing, their regular back-end systems, because they are not getting replaced. Right? T-Mobile is not going to change the whole business model to blockchain. They will only have an adapter to a blockchain, like if you'd have an adapter for a JMS adapter for a messaging system or something like this. And they'll process, and at some point in time later, they'll send a response transaction. They express a statement. They just say, okay, we have checked this, we have talked to our clients, everybody's okay, let's do this. And in practice, these are of course not verbal statements like this, but they are transaction records, be they JSON encoded or binary encoded, but this is just machine readable information. Okay, so that's the lowest level on which we start. As soon as we have these transactions in our blocks, what's important is that globally, they are in a strict sequence. So every node, every participant sees all the blocks in exactly the same sequence, after all the transactions in the same sequence, because they will be put in blocks and the blocks are in a sequence, and inside of the block, the transactions are in a sequence. So we don't have to do later stage reconciliation just to find out which transaction came before and which came after. Parts of the data can be encrypted, of course. So we can send data so that only the receiver will be able to decrypt it. If we're looking at our number transfer sample, we would never, in a real network, we would never persist the customer's name and date of birth on a public blockchain. Because it's just by current law, that's not something which we could do even if we'd want to. But we might put into our threat model, we might find out if some kind of encryption is enough or not enough. Or we can put hashes to external data on a blockchain. We can, for example, in addition to just saying, oh, this client's in front of me and they say they want to port, I could scan the contract which I've signed. I could create a digital hash code, a checksum over the PDF, and I could put this into my transaction. Why would I do this? Well, so if later somebody challenges my statement, basically says, well, I don't believe that you actually had this okay from our client, they could go back to their enterprise system, retrieve the scanned contract with this ID, and send it over to the regulator to verify this. The regulator would run their own hash code calculations, same hash algorithm, and could verify that these are unchanged. Or, and that's what, for example, Hyperledger Fabric or Quorum does, you can send the data point to point, so you don't even put the actual data on a blockchain, not even in encrypted form. You send it point to point and only put a hash code to this point-to-point transaction on a blockchain. So you send it in the first stage, you go directly from telco B to A, send the information, and then in the transaction here you only send the hash code of the existing data. And the node would process it. Every node would see this information, the fact that you are transferring this phone number, that's in the public part, but you would not see who owns the phone number. And even if the encryption was weak, there is no way to find out who owns the phone number in this case. Okay. Hyperledger Fabric or Quorum do this out of the box so that you can basically just set a flag on your transaction that you want to opt into this behavior. It's not something you have to implement. Okay, so what we have now is the absolute bottom level of information and of topology of a blockchain. And this is, we have a replicated, immutable, within technical boundaries, of course, sequence of transactions. Within technical boundaries means if, I don't know, 10 people here create a blockchain, and all of us would agree, we could, of course, change any transactions in the past. This is what's called a hard fork in blockchain terminology, usually called hard fork, which means that we have to agree manually that we want to change information in the past. This has happened a few times on Ethereum and on Bitcoin, for example. When all the miners agreed that or a significantly large portion of miners agreed that they want to roll back a certain transaction. They really have to change the program code, redeploy it, and then you'd have some kind of mutability. Okay, so where does code come in? As I said, that's just the lowest level of semantics, the lowest level of information. There's no semantic yet. I say that, well, transfer the number, and the other side says, okay, transfer it. Okay. How does the system check if the statement is valid? Because otherwise, I could be telco B and I could say, well, we are okay, you can transfer this number, while the real owner of this number would stand at the side and say, whoa, stop, you can't actually transfer this number. If we're only looking at the statement by statement level, there is no code yet, there's no business rule yet to implement this. How do we fix this? Well, in one of two different ways. We can solve it by laws, contracts, and penalties. That's the regular way how we reconcile in business to business today. If we are not looking into blockchain, basically what's happening is you call my web service to tell me to transfer something, and if I figure out later on that you didn't have the right to transfer this, there will be a penalty assigned to it. Or the Bundesnetzagentur, the regulator, will put a fine on you, which you have to pay. That's a post-fact reconciliation stage. We want to avoid this, and that's one of the powers of blockchain technology, is that it allows us to get not just shared data, but shared distributed code execution. And that's the technological approach to solving this. And now we are moving this challenge from a post-fact reconciliation, which we could do with any database, to a pre-fact reconciliation, where we say, well, if the statement doesn't make sense, we don't even allow it on the block. And this is what smart contracts are. So that's number two of the things which you should take out of this session. A smart contract is nothing but a rule which specifies whether or not the transaction is valid. I like to put this up front, or put this in front of you, because if you read the hype in business magazines, you constantly, on a daily basis, read things how smart contracts will revolutionize healthcare, or they will totally change the energy sector. And we, as technicians, as developers and architects, we have to be aware that a smart contract as such doesn't change anything. It's a piece of code which is ran on multiple nodes. And to check the validity of a transaction, it can usually, that's true for most blockchains which we normally work with. They read and write the word state. And in our number porting sample, the word state could look like this. It's a simple key value database where we have the phone number as the key and the current owner as the value. Now I'm simplifying things here. You wouldn't have the string telco C in practice in your database. You would have, for example, the public key of the current owner, so that later the current owner you can verify a transaction by verifying its signature against the public key of the one who should sign it or the one who's allowed to sign it. Okay, so we have the word state. Now if we zoom into one particular node during contract execution, that's what we would see. We would start with the current word state. By the way, when we initialize the smart contract for the first time, the word state is empty. There is no pre-assigned number in there, unless we programmed our smart contract to be this way. So even the initial assignment would have to be done via transactions. So we could, for example, we would do is we would create our contract so that our regulator, the Bundesnetzagentur, has special permissions, and it has the special permission to create new numbers and to perform the initial assignment. Okay, and then we have our statement, again expressed in machine-readable terms, and we have our smart contract. Now this is pseudocode, but this pseudocode is very close to Solidity, the programming language which you would use on Ethereum. The only difference is that I did not specify the data types here, and this was just for reasons of space. The rest is more or less Solidity. So it's really, when I say we're doing a cryptographic verification, it is really just a simple comparison. Solidity and Ethereum does this behind the scenes. And the first step is, when you get this transaction, is that every single node will run through their smart contract code and will perform the logic. It will, at first step in this contract, perform a cryptographic verification whether or not the signer of the message, of the transaction, is the current owner according to my word state. In this case, it is not, because we have the fake telco which tries to say, okay, you can transfer the numbers. So that our program code would throw an exception and the transaction would be marked as invalid. And now it depends on the blockchain tooling which you're using. Some of the blockchains will take invalid transactions and include them in the block to specify that you tried to execute an invalid transaction, and also to take your money, because contract execution usually costs some kind of cryptocurrency in these networks. And others will just abandon it and will never include it in the chain. So that's one thing where these tools differ. If a correct message reaches our smart contract, so we have it now signed by telco C, which is the correct owner, the same code will execute, we perform the same cryptographic verification, but this time we have a match. And again, this would be a signature, a cryptographic signature, and this would be, for example, the public key for the signature on a conceptual level. And in this case, okay, it matches, so we can change our word state. And after the word state is changed, we see, okay, the new owner is now telco A. And it's literally, that's the code you write. Solidity and Ethereum would persist this information behind the scenes automatically. So you don't have to write database access code here. Okay. What's important? Well, it's important that for this to work, all of the nodes have to have the same version of the smart contract, because you don't trust the other nodes. So every node has to perform this verification. What does this imply? Well, first, how are they deployed? Okay, they can run inside of a node. They can run, if you're running Ethereum or an Ethereum derivative, the smart contract virtual machine is part of the Ethereum node. Every Ethereum node contains or is directly linked with an EVM, an Ethereum virtual machine. To deploy a smart contract on Ethereum-based networks, you would just send a contract creation transaction. And when I'm talking about Ethereum-based networks, I'm also referring to, or maybe especially referring to, Ethereum-based networks which are private networks. So you have Ethereum, the public chain, but there are also an unlimited number of private chains which we don't see running on the same software, just configured to use a different consensus algorithm so that we don't have mining. But it's the same software. You can run the same Solidity code with it. Okay, so I'm sorry, it's getting quite hot in here. I don't know if I think you agree. So I don't know if there's any AC connector, but I don't see one. So, but if anyone sees the AC controller, I think it would be helpful. No. Okay, so we just have to keep going for the next 20 minutes. I hope nobody falls asleep. I'm not mad at you if you're falling asleep. Based on my huge inflated ego, I would just put it off to the temperature. So I would just say, you're not dissatisfied about the talk, it's just the temperature. Let's just keep it at this. If this is not the case, don't tell me. It's okay. And no oxygen is horrible in here. Okay, or we can run smart contracts in a separate process. That's what, for example, the blockchain tooling Tendermint does. So Tendermint says you have a blockchain process which you configure and which connects to the other nodes, and you have your application logic which uses an interface called ABCI, Application Blockchain Interface, to talk to this process. And you'd have to start this process explicitly, etc. So here, for example, if everybody agrees on the network, you can just change the code inside of a smart contract after the fact. In Ethereum, a smart contract per se, an individually deployed smart contract is not changeable. So you have to follow specific strategies to get code versioning so you can run updates on them. Or you run it inside of a managed Docker container. That's what Hyperledger Fabric does. Behind the scenes, it will automatically start one Docker container for each smart contract, which they call chain code. And it will open a socket connection. So it's very similar. So depending on the tooling, your smart contracts are executed at different places. Okay, so we have one missing link so far. We know that there are smart contracts. We know that there are of course, blocks and transactions. We have two missing things. So the first one is, how do the transactions actually get into the blocks? And now this differs between all the blockchain tools, but I'm going to illustrate how it works on Ethereum-based tools, because conceptually it's very similar. We have different phases in which a transaction can end up in the block. Okay, I'm zooming in again. We see a subset of our network consisting of 3 different nodes. And all of them have the same world state, they agree, and everything's fine. We have a memory pool in each of our nodes. So if somebody wants to send a transaction to the network, they connect to the node that they know using their credentials, as in the image before, and they'll send a signed transaction to the node. Now, on Ethereum-based networks, nothing happens at that stage. It's just collected inside of a memory pool. And it's replicated. The memory pool is replicated. It's not securely replicated, so it's only a best effort replication. So if you look at the real Ethereum network, which usually has about 20 to 25,000 nodes online at any time, every node will see a different version of the mempool. Some transactions will be synchronized, some of them won't, and the network doesn't mind. I'm going to talk in a second about what's the next step. Okay, so if another transaction enters the system, it could start from another node, and it will also be broadcast. And the same, of course, if this happens more and more. Now, we're starting with a pool of 3 different transactions. Important, they don't have sequence numbers yet. They just exist in a huge pool. On Ethereum public network, this pool can easily be hundreds of thousands of entries, transactions waiting to be handled over time. But as we've heard before, it's only 15 transactions per second. So depending on what you pay, because Ethereum uses an auction behind, more or less an auction-based system, depending on how much you pay, your transaction will be handled quicker or slower. If you pay really, really little, it could well be that it's never handled. So it is in the mempool, it will be replicated, but nobody's ever touching it. So in Ethereum, you can increase your bid later on to increase the chance for it to be handled. Okay. So now we have our consensus algorithm, our mining, or our proof of authority round, and it figures out that node 1 is the selected node to create the next block. And I'm simplifying things a bit here, but conceptually it's perfectly okay. So we know that this node is now the one which can create blocks. So what this node will do is it will look into its personal mempool and pick out the transaction it wants to include in the block. Based on the pricing or the complexity of the smart contract execution, the node can decide and can say, well, you're not paying enough, I'm going to use some other transaction. And then it takes one transaction and puts it into a temporary representation of the next block. So we are talking about block 21 now. Before we had, oh, no, that's certainly not how it should look. Before we had block 20 as the maximum block number for every node. So block 21 is the one we are building right now. As soon as I include it in a block, it gets a number, it gets a sequence in the whole set of transactions. Even if this is just temporary. So it's only valid for my view of the world. Okay, and then the smart contract is executed. And in our case, this was our bad smart contract. It's failed. The transaction is failed. It's still in the block, but it is failed. And then I take another transaction and I execute the smart contract again. And oh, in this case, it's okay. So I change my word state and I put it into my block. And at some point in time, I reach a block limit. That depends on the network configuration, which basically says how many transactions or in some way I can put into a block. And I calculate the block hash and I start to replicate my block, well, this which is now closed. And I start to replicate this over to, where am I? To the other nodes. And now the important thing is, the other nodes, upon receiving this block, will perform the exact same smart contract calculations. And if they mismatch, they will not accept the block. So for example, if we would be a malicious telecommunication operator here, and I run a private version of my smart contract, which has changed the owner so that I can actually be okay with the transaction, and I run this on my side and I get an okay on my side, and then I replicate the block, then these will also execute the same block and they will reject the whole block. So if I'm a miner and I've invested a lot of time and money into my mining hardware, by doing this, I'm essentially letting this money which I've spent go to waste, because everybody will reject my block. So I've just done a very dumb move. And that's how Ethereum and Bitcoin keep the system honest. By saying, well, if you're trying to attack us, it's not going to fly. You're just going to lose your money. Okay. This is like, if you have a bank account statement from which your regular bank sends you and it says you have this amount of money, and you take your bank account statement, you scan it in your computer, you put a 0 at the end of your bank account statement to have, just tenfold increased your assets. And that's fine. And you're looking at this and you say, yeah, I'm really rich. And then you take this, walk to your bank and say, please give me the money. Okay, it's not going to work. It's exactly the same thing. The worldview doesn't match. You can always change your view of the world, but the other ones, they don't count. And there are 25,000 other ones. Okay. So if we have smart contracts which have to be the same for every single node and which have to be executed in a deterministic way, we have one problem. How do we work with external data? So how can we work with data in our enterprise backend system or in our existing web application? And the answer is you always have to do this in two different steps. There have to be two transactions whenever you work with an external system. Somebody says, oh, please find this information in my database. Find out who is the customer with the ID 1234. What's their name? And on the other side, you have a process running which listens to these kinds of events, takes the information, the request from the blockchain, processes it, and sends a signed response answer to the original requester. Because otherwise the other nodes could not verify your claim. But this time we have the ability to get a deterministic execution, because the other nodes, they don't have access to your internal system, so they can only access on-chain data. So you have to move data on-chain. If this is trusted or not or incorrect is a separate question, but technically it has to be done in this way. Why is this important? And that's mainly important right now because these things are called oracle. So whenever you hear oracle in the blockchain context, usually it's not referring to the company. It is referring to this concept of having somebody listen to events, go to the outside world, and send data back. Okay. So our conclusion for this technical part is that we now know that a blockchain is a replicated, nearly immutable sequence of transactions which also conform to certain rules. And these rules are called smart contract. So let's go on to the next question, which might be quite interesting, is what can we do with this? Because right now we have a nicely replicated data structure which allows code to run. And when we talk about this with business developers mainly, who are not out to create a new ICO and make money out of the ICO, but who are looking into real business use cases. Business in this case also means selling in-game items in a game. But it's really about the business case. So what are the use cases we can get? And there are 3 different classes we like to talk about, or I like to talk about when we as in my company, when we work with projects or when I work with projects. We have 3 use cases, and that's also how we recommend developers to approach this subject, because they're getting harder and harder. So the first use case, and that's the simplest one, everybody starts with this one, is a documenting use case. You're just time-stamping information. This means that you have a piece of information, you calculate a hash code over this information, and put it on a public blockchain, for example. It's very simple. You can do this in, I don't know, something like 15 lines of code or so. But by doing this with the small number, with the really small number of lines of code, you can prove the existence of the data and the integrity of the data, the fact that it has not been changed from the point of creation of this block. And that's something quite nice, because we are using this in systems with our clients who have to create audit trails or audit safe document storages. And in the past, you wouldn't solve this on a purely technical way, but one part of your audit safe record storage is an organizational measure, which basically says you give, as a CEO, you give a signed document to your system administrator and say, you, dear system administrator, you are not allowed to change the data. That's how you go through certification for audits proof systems today. So you have a whole technical layer which says, oh, here we check the username password so that nobody can access it, etc., etc. That's our code which runs. Oh, and at the end, we tell the administrator they must never change data. Okay, so there's always a little bit of a hole in this certification process. Or you're using extremely expensive hardware solutions. Now, with this, you can experiment quite easily to put information like this on a blockchain. You can combine multiple documents in a single block so that you don't have to pay transaction fee for each document, etc. And then you end up with, I don't know, having to pay something like 2 or 5 euros per day for an unlimited number of audit-proof documents. So that's a very nice one. A lot of companies are doing this because it's very easy. And you can later use it to verify the existence of a contract. Or you can imagine if you have a bidding system, if you are a company and you're looking for suppliers for something, normally, there's this phase where they can send in their bids. All the companies, you ask for a request for bid or a request for proposal, and they will send the proposal to you. But of course, as soon as you have the proposal, you can look at it, or your employee could look at the numbers and could go to their friend at a different company and say, our current lowest bid is 10,000 euros. If you offer us for 9,800 euros, you are the one who is choosing. So you can work against the system. And using this, you could, for example, in the first phase, only send hashes of information around, and in the second phase, send the real bid, which means that employees could not read the bids beforehand to share this information. You get a quick ROI as a company on this one. The reason you do this is because you don't have to think about smart contracts. Usually these systems are very small in terms of smart contracts. There are only a few lines of code, and they don't have a governance process, because in this point in time, it's only you as a company and the public network. Okay, so that's simple. That's easy to get started. And then we have collaborative use cases. These are the ones in the business-to-business world today. Everybody is doing this right now. So we are talking about, syndication of loans, of credits between multiple banks and a large lendee who wants to borrow the money. And what they do is they put data exchange between companies on a blockchain to achieve process transparency. That's what we've seen with our number porting. So number porting is certainly a category 2 use case in this case. You just put states of your processes on the blockchain so that you have a shared view of the world. That's the idea behind this. We don't have to do reconciliation if we share the view of the world right from the start. This digitizes paper processes. It's not magic. It's not going to make you a millionaire in the next ICO. It's just going to take a few percentage points or parts of percentage points off your process cost. So it's all, again, relatively easy. Companies are doing this. Phone number porting would be one example. Actually, I've been using this as a sample for quite a while, as a use case. And the UK announced just 2 or 1 actually weeks ago that they are now starting to really look into this. Their regulator looks into doing it this way. In France, you have the loi Armand, which allows car insurance to be ported between different providers there's a law which forces the providers to allow the porting, like we have it with phone numbers. And there is a company we work with. They've implemented this for 14 of the insurance companies on a blockchain-based process. And then we have the interesting ones. From a technical point of view, the ones I'm most interested in are the last group. These are the ones where we create new markets, where we can do things not just cheaper or more quickly, but where we can do things which we can't do today. And one reality check before we go into this, they are incredibly more complex compared to the first two. Because now you have to talk with multiple people and multiple corporations, and you have to find an agreement. And usually the multiple corporations are competitors because you want to create additional value so that the sum of the competitors' individual process is lower than what you achieve with them sharing data on. It might be a blockchain, it might be some other way to share data, but the idea is we're getting competing companies to share data so that they can create new markets. A sample I like to use for this, the use case is the car insurance industry. Now in Germany, car insurance industry, the risk evaluation of a car insurance industry is based on the number of years you didn't have an accident. So if you have 10 years without an accident, you get the accident-free class 10, for those who are not in Germany. And it's based on car ownership, not on driving experience or anything. So we have a new problem. We have car sharing as a new concept. And in my company, a number of our employees don't own a car. We are based in the city, and we are in Karlsruhe. We are the car-sharing capital of Germany. But in all over Germany, we have over 2 million users of car-sharing. Now, what does this mean? This means that if you're a student living in the city, you don't need to own a car. It's perfect. However, if you are 35 now and you want to have kids and you decide to move out of the city, you have to buy your first car, and the car insurance will tax you as if you are a total beginner at driving. Why do I know this? Because I'm Austrian, I'm living in Germany now and have lived in Germany for 15 years. And when I moved to Germany, I did have a car before in Austria. And I moved to Germany and I got a new car. And I could only get the worst possible rate because I was a beginner in terms of German insurance. I was a beginner, I have no experience. And they wouldn't accept any of the Austrian information. So we have a interesting situation. I ended up having to pay 3,500 euros for my car in the first year. So we have a certain market here. And if an insurance company would have offered me some way to prove that I've been safe in Austria, I would have picked this company. So they would have been able to increase their market share. I would not have looked into who is the cheapest insurance agency. In total, I would have looked into who is the cheapest for my particular very special use case. And now we have the same thing for all car sharers. They don't know this yet, but if you are a car sharing user who doesn't have a car, 15 years from now, you will pay for this. Okay. Now we want to share this information. We want to be able to find a way to share accident-free kilometers or accident-free time from multiple providers, because you are in Stadtmobil, you rent a car by 6 or budget, and etc., etc. And you want to be able to use this information to give it to your insurance agency so that they can give you a better price. We want this to be GDPR conformant. DSGVO in Germany, we want this to be possible in terms of sharing data between companies. As you know, in Europe, we have very strict laws. And it should scale. So we don't want to develop point-to-point interfaces from one insurance to one car service, car sharing provider. And the data should, and now that's an interesting thing, the data should survive bankruptcy of a party, or the fact that a party wants to leave the network and says, I don't offer this information anymore. Why? Because we are now starting to accumulate information for 15 years. The car sharing provider which I use today might not exist in 15 years. But I need the information in 15 years. Okay, so that's the starting point. So the easiest solution on blockchain would be the following, which is not correct. So it would be, say, well, we have a car sharing provider, we have a customer somewhere. The customer has or generates a digital ID, a private public key pair, for example, with their browser or using a membership card or something. So we find some way to create a public key pair. And the customer goes to the car sharing provider and uses their public key. All of this will be in browser. You won't see this. The user doesn't see that there are public-private key crypto. So, you know, my grandmother would not be able to do this otherwise. So we have to make this simple. Register at the site and link it to your customer ID. And from that point on, our car sharing provider could put monthly statements of how safe a driver I am onto the blockchain. You could say, in May I did customer ID X, did this a number of kilometers, etc., etc. Now that's not flying. We cannot share this information this way, in an immutable way. We have a right to be forgotten in GDPR. So every human being has the right for her or his data to be removed. Doesn't fly with blockchain. So a lot of projects stop here and say, well, we can't do this on blockchain, it's fine. And you shouldn't stop here. Because what you could do is, you could, for example, that's only an example, you could encrypt the information which you store on the blockchain with the public key of the customer. Every piece of information for different customers is encrypted with their own public key. So if you put information on the blockchain, nobody can find out patterns, can track me, etc. The only thing I could do is I could decrypt all of this information. And all of these blocks, before they are encrypted, they will be signed so that I know who put this statement out on the blockchain. And I can then take this and hand it to my insurance provider. Even 15 years after the information is logged on a blockchain, I can use it to talk to a provider. And if we scale this to multiple providers, and that's where it gets complex. That's the part I mentioned before, but it's getting complex. You have to talk with multiple stakeholders. Because what they will do is they will share one blockchain, or there might be competing ones. But the idea is that you have a number of blockchain systems, and not one for each provider, not one for each insurance agency, because then you could do it with the database. Okay, so we're storing the information, all of them storing the information. This is, I don't know, this is my car sharing provider, that's a rental cat provider even. Now that's pretty nice. And but this was the only bug on my slides, right? Let's see if I forget this, or I have to change this later on. Okay, so we're putting all this on the blockchain, and my client, my customer, can take all the data which belongs to her and aggregate this. We could, in theory, have different private-public key pairs for each individual service provider to even allow the compromise of one key to not compromise the rest. In fact, there are more approaches. There are approaches called zero-knowledge transfer, zero-knowledge proofs. So here, what we see here, that's where today's reality ends. That's something we can do today. You can do this on a blockchain today. There's nothing magic here. Actually, you could do a proof of concept in a couple of weeks for this. On the technical side, not getting everybody to agree. But if we look forward, things will be different. The research currently is working around a concept called a zero-knowledge proof. That's the idea that an insurance company can say, well, to give you this nicer price, I need you to prove somehow to me that you have driven more than 10,000 kilometers without an accident. They can formulate in a descriptive programming language a proof A piece of code, some rules encoded, which specify this proof. And I, as the customer, will run this proof, this zero-knowledge proof, on my environment. There's maybe a virtual machine for running this programming language. And what it will do is, it will access the data, only my data, the data which I can see. It verifies the signature for each piece of data, and it provides, I don't know, it accumulates the sum of kilometers, and the zero-knowledge proof is a function which essentially returns true or false. So at the end, my code here returns true or false, and I can go to the insurance company and hand them the proof. Now the proof here is cryptographically safe, which means that I can only do this if I really have the set of data to perform this calculation, even though I never give the data out to the third party. And that's the ultimate privacy. So at first, privacy and blockchains look like they can't ever fit together, because, you know, it's immutable public information. There's no right to be forgotten. Here we are talking about things where data is encrypted in a way that I can run a zero-knowledge proof. I can derive information and hand the derived information to a requester without ever showing them all my information. So they cannot derive patterns or who I used, which provider I used, etc. But they can still get a confirmation that I have this amount of safe driving experience. Okay, and with this we've reached the end of the session. As I said, these are the three types of use cases. And if you're starting out in this field, make it easy for you. Start out with one of these two to play around with, to find out how the technology works. Starting out with these might be hard, because you have to get parties on board to actually do this. You have to get companies to sign up with you. And if you've got any questions, I will be around here. If you've got questions later on, I'm on Twitter, I'm reachable by email, and you will find the slides on Speaker Deck within the next hour or two. Thank you very much.